Here are two geometrically similar objects, both spheres. This plastic ball with a diameter of 0.60 centimeters. And this is a helium-filled balloon with a diameter of 100 centimeters. By adding various weights to the balloon, we carried out a series of experiments, in each of which the terminal speed of ascent had a different value. In one of these experiments, the terminal speed was 5.4 centimeters per second. And you recall that the diameter is 100 centimeters. We dropped the plastic ball in water and measured its terminal speed of descent. It was 55 centimeters per second. And you recall that the diameter was 0.60 centimeters. Now we may combine these numbers for the density, the speed, the length, and the viscosity, according to the Reynolds number formula. For the helium balloon rising in air, we found that the Reynolds number was 36, while for the plastic ball falling in water, the Reynolds number was 37. You can see that for the experiments we selected, the Reynolds numbers differed by only a few %. So while these two experiments, one in a gas, one in a liquid, appear very different to the eye, they are in fact similar, dynamically similar. And as you will see later, from a measurement of the drag of the plastic ball in water, this similarity enables us to predict the drag of the helium balloon in air. This idea of dynamic similarity is the very basis of wind tunnel testing and other forms of model testing. It is the key by means of which we can predict, from measurements made in the wind tunnel on a model airplane, the forces which the real airplane will experience. The Reynolds number shows us something else, for it is a measure of the ratio of the inertial forces to the viscous forces in the force balance. Very, very low Reynolds number, for example, means that the viscous forces are so large compared with the inertial forces that the inertial forces may be neglected. We then have a balance between the net pressure force pushing on the fluid and the net viscous force resisting the deformation. Very, very high Reynolds number, on the other hand, means that the viscous forces are so small compared with the inertial forces that the viscous forces may be neglected. We then have a balance between the pressure force pushing the fluid and the inertial resistance to acceleration. To summarize, very, very low Reynolds number means highly viscous behavior. Very, very high Reynolds number means only slightly viscous behavior. We've talked a great deal about the forces and the motions and how they are related for typical fluid particles. But now how about the forces acting on an object, moving through a fluid or stationary in a moving stream of fluid? The important idea here is that these forces are exerted on the surface of the object by those fluid particles which are in immediate contact with the surface. On every element of surface area, the adjacent fluid particle exerts a normal force and a tangential force. In general, these two forces have components in the direction of the oncoming flow. Let us look first at the frictional forces. you can see that over most of this body, the tangential forces are nearly parallel to the direction of the oncoming flow. Thus, they contribute considerable frictional drag. Now let's look at the pressure forces. At this point near the nose, the pressure force normal to the surface incorporates a positive drag component. At the shoulder, the pressure force has zero drag component, while here near the tail, the pressure force has negative drag components. That is, the horizontal component of the pressure force actually thrusts the object against the flow. Adding up all such components for all elements of the body's surface, we get two contributions to the total drag: pressure drag and friction drag. Friction drag is always present because all fluids have some viscosity, but the pressure drag may be either very large or it might be quite negligible. Which it is depends on the difference between the average pressure on the front half of the body and the average pressure on the rear half of the body. If the average pressure on the rear half is equal to the average pressure on the front half, then the net pressure drag is zero. But if the average pressure on the rear half is much less than the average pressure on the front half, then there is a large net pressure drag. The reason for thinking separately about these two types of drag is that they arise for different reasons, and since one or the other may predominate in different ranges of Reynolds number, it is not so surprising that there are different and distinct types of fluid behavior. Let us go back over the ground we have covered. We conceived the model of a continuous fluid, and then we focused attention on one of the many very small lumps forming the entire body of fluid. We noted that body forces and surface forces act on every such fluid particle, but that in our experiments, the body forces could be set aside, leaving only the surface forces. We resolved the surface forces into two components: pressure forces acting normal to the surface and viscous forces acting tangentially to the surface. We saw that these forces control the motion of a fluid particle through Newton's law, which relates the net pressure force on the particle and the net viscous force to the inertial resistance to acceleration. Then, by thinking about two extreme cases, fluids of very small viscosity and fluids of very large viscosity, we were led to a most useful idea, the Reynolds number, which allows us to categorize the type of flow in terms of the relative importance of viscosity. Finally, we recognize that the drag on an object, like the forces on a fluid particle, could be divided into two parts: pressure drag and viscous drag. This set of ideas is a powerful tool for interpreting and explaining experimental observations.